Hello, Sebastian here. Welcome to the sixth episode of Learning Game Development. Let's just hop right into it. But first things first, actually, before we hop right into it, so not let's just hop right into it, whatever. It is a little bit late. I wasn't really feeling too well, and I know I could have probably just not done an episode today, but I do want to stay committed to doing this every day except for Sunday because Sunday is kind of the off day. So that's the explanation. It is 11:08 currently. So uh, kind of a lot later than I usually record, and also I want to get to sleep earlier than this, but I'm trying. Um, but here I am. Learning game development, I'm committed. I really want to go hard on learning game development. So I'm here. Let's get it.
Hello, in this episode we're going to look at two very basic trigonometry problems which crop up quite frequently when making games. The first problem
Okay, so I will probably already know a lot of this. Um, I may not remember everything exactly as it is supposed to be, but I will remember some things. So this is going to be a little bit of a refresher.
is if we have some angle, say for example 120 degrees, how to calculate a direction vector from that. The second problem is just the reverse operation. If we have a vector pointing in some direction, how to calculate this angle.
Okay. Was there not sine and cosine? So angle should be... Oh. Cosine, sine, I don't remember. I don't actually remember.
Along with solving these two problems, we'll also be looking at how to convert between radians and degrees, and how to actually use these trig functions inside the Unity game engine.
Sure.
Alright, let's start with a unit circle, which is just a circle with a radius of 1 centered at the origin. So if we create a pair of axes, the circle obviously cuts the x-axis at x equals -1 and x equals 1, and cuts the y-axis at y equals -1 and y equals 1.
Yes.
We can also label the angles, starting with 0.
Okay, why do you need... I mean, it is useful, probably. Isn't there arc sine? Isn't there like opposite sine and opposite cosine?
Degrees here on the
I forgot. I honestly forgot a lot of trigonometry, actually. So ignore what I said earlier.
right, and increasing anti-clockwise. Okay, now say we have a vector pointing in some direction, and all we know is that this angle over here, which we'll label
Anti-clockwise. Okay, yeah, anti-clockwise, not counterclockwise.
theta, is equal to 120 degrees.
Lol.
We're trying to find the coordinates of the point where the vector touches the circumference of the circle, since those values are of course the x and y components of the vector. By drawing in these components, we get a nice right-angled triangle. Now, I want to emphasize that it's technically incorrect to think of x and y as being the lengths of these two sides of the triangle, since lengths, of course, can't be negative. However, I like to think of them as representing the side lengths anyway, and I'll be referring to them as the lengths in this video, since I find it to be the most intuitive picture. Alright, time to introduce three trig functions, sine, cosine, and tangent. As you can see, the sine function takes in the angle theta, and calculates the ratio of functions sine, since I find it to be the most intuitive picture. Alright, time to introduce three trig functions, sine, cosine, and tangent.
Yeah, so this is the refresher here. Got it. Sine is... Oh. Wait a second. What? That's not right. That's not right. The angle, it would be the sine of this angle. So 60. Like, this would be something else. Like, it can't equal 120. Without, I mean... Can it? I thought it was a right angle. I thought these only work for right angles.
As you can see, the sine function takes in the angle theta and calculates the ratio y over the radius. Cos calculates the ratio x over the radius, and tan calculates the ratio y over x. So if we
Does that actually work?
want to calculate this y
Maybe.
value, we can use our sine equation to write y over r is equal to sine theta. Since the radius of the circle is equal to 1, we can simplify that to y equals sine theta. And we can likewise write that x is equal to cosine theta. So that is in fact the general solution to this problem, our vector points in the direction cos theta, sine theta.
Uh-huh.
In this example, we said that theta is 120 degrees, so we can just use a calculator to find cos 120 degrees equals negative a half, and sine 120 degrees is about 0.87. Before we move on to the second problem, I'd like to look at the graphs of the sine, cosine, and tan functions.
Oh, I guess it does work for any angle. Never mind. Wait, so here sine would be 0? Yeah, I need to brush up.
So we saw that sine theta is simply the quote-unquote length of this blue line, and cos theta is the length of the green line. From this animation, you can see how these...
Oh, okay, here it
cos
is.
theta is the length of the green line.
Yeah, yeah.
From this animation, you can see how these values...
Okay. Oh, okay. Okay.
So we saw that sine theta is simply the quote-unquote...
Oh, negative. So it does equal negative. Because it's on the unit circle.
length of this blue line. These values change
So
as theta increases.
Yeah.
So plotting the length as theta increases.
Okay,
So,
and he's literally just gonna
plotting
plot
the length of the blue line.
He's just gonna plot the waves. He's just gonna plot the sine and cosine waves. Crazy. Yeah, this is like crash course introduction to trigonometry right now, pretty much.
Theta goes from 0 to 360 degrees. We get a plot of sine theta.
Beautiful.
We can do the same thing for the green line, cosine, and we'll notice we get the same curve just offset by 90 degrees. From this, we can tell that sine theta is equal to cosine of 90 minus theta, and
offset by 9. Oh.
Conversely,
yes.
Cosine of theta is equal to sine of 90 minus theta. Now, what about the tan graph? Well, tan theta gives us the ratio y over x, so it's equal to the blue line divided by the green line. This means that tan theta is equivalent to sine theta over cos theta. Anyway, let's plot tan theta. Unlike sine and cosine, which are both in the range -1 to +1, tangent has a range of -infinity to +infinity. Okay, we're going to come back to the tan graph in a moment, range of -infinity to tan theta.
What?
Unlike sine and cosine.
Oh, yeah, because it equals 0. I've actually never seen tangent. I've actually never seen tangent graphed. Or have I? Have I, but I've just forgotten.
Which are both in the range -1 to +1, tangent has a range of -infinity to +infinity. Okay, we're going to come back to the tan graph in a moment, but for now let's take a look at problem number 2. In this problem, we know the x and y components of our vector, and we're trying to figure out the angle. So in this example, we know that x is equal to -0.71, and y is equal to +0.71. Let's try solving this using the tan ratio. So tan theta is equal to y over x, therefore in this case tan theta is equal to 0.71 over -0.71, which of course
Is
just equal to -1.
-1.
Let's head over to our tan graph and see if we can use it to figure out the angle. If we look at where tan theta...
Okay, whoa. I mean, it's just gonna be... what is it? It's just gonna be 135, right? Isn't it just gonna be 135? Yes.
Theta is equal to -1 on the graph, we'll notice that there are two possibilities. Either theta is equal to 135 degrees, or it's equal to 315 degrees. In this case, we can tell by looking at the diagram that the correct one is 135 degrees. Now, obviously, you won't usually be manually looking up the answer on a graph. You'll instead use the inverse functions, which are arcsine, arccosine, and arctangent.
There you go. Yeah, true.
Now, these functions will just return one of the two possible solutions, which is a little bit inconvenient, and it's for this reason that many programming languages have got an extra function called atan2. Instead of taking in the value of y of x, it takes in the y and x values separately. To see why this is helpful, let's divide.
Okay. Yeah. Because the other one would be over here, and then it would be positive x, negative y.
Our circle into 4 quadrants. Obviously, y is positive in the top 2 quadrants and negative in the bottom 2, while x is positive in the 2 on the right and negative in the 2 on the left. So if we use that atan2 function, passing in 0.71 and negative 0.71, the function can see that the y value is positive and the x value is
Yeah.
negative, meaning that
Yes. Yes.
the answer must be in quadrant 2. By narrowing the search down to a single quadrant, the function is now able to find a single correct answer. Alright, so the general solution to our second problem is that theta is equal to atan2 of y comma x. Okay, so having covered the two problems we set out to solve, I'd like to move on to radians. As you may know, radians are an alternative to degrees as a way of measuring angles. The idea of radians is as follows. If we create an arc with the same length as the radius of the circle, the angle that it makes at the center of the circle is equal to 1 radian. If we keep as the radius as a way of measuring angles, the idea of radians is as follows. If we create an arc with the same length as the radius of the circle,
Okay. Sure. That's gonna be some weird. That's gonna be some weird thing with a decimal. 2 pi r, so that would just be 2 pi. It would just be tau. Um, I guess, yeah.
the angle that
He's gonna probably say
it
that.
makes at the center of the circle is equal to 1 radian. If we keep going around the circle, you'll see that we can
Oh,
fit
the angle. Okay. I was saying, oh, 2 pi r. Wait. No. 2 pi r, which would be 2 pi. Okay, that would be the total thing divided by, so it would be like, wait, it would just be 1. So it would be 1. So there are going to be like 6 and, 2, 8. 1 point. Okay, 1 for 3.141. Is it 159? 3.14159? I don't care. I think it is. So it's going to be like 6 and a little bit, and a quarter,
about
roughly.
3.14 of these arcs into a semicircle. More precisely, of
Okay.
course, that figure
So what? So sure.
is pi.
Like what? What? Okay. Got it. Pi radians in. There are always pi radians in a triangle. Pi radians. Yes. That's the easiest way to say it. There are always pi radians in a triangle, or the sum of all angles in a triangle. The sum of all, yeah, of all angles in a triangle equals pi radians. Yeah, I don't like radians, bro. Why?
So 0 degrees is simply
Whatever.
0 radians, 90 degrees is pi over 2 radians, 180 degrees is pi radians, 270 degrees is 1.5 pi radians, and once we reach 2 pi radians, we're back to 0. Knowing this, we can easily convert from degrees to radians by multiplying by pi over 180, and to go the other way around by multiplying by 180 over pi.
Convert degrees to radians. Multiply by pi over 180. That just seems extra, though. Pi over 180? Oh, I guess, yeah, that is.
Unity's trig functions all work.
Okay, no, that's how you do it. It's not extra. I'm thinking like you don't have to put a 180. You could just do something with pi. But no, that's not true. No, no, that's not true. Oh, whatever.
Radians, as we'll see in just a bit.
I mean, pi over
Over pi
180 equals something. So that equals something. So you just, I don't know what that equals. Um, pi over 180, it equals like, yeah, it equals something small, some really small number. It's let me think. Can I do this in my head? Can I do this in my head? Do I have enough brain power currently to do this in my head? Um, so it's gonna be less than 0.1. Okay. Let's just look at it as 18. So let's do, I'm overcomplicating this. 314 divided by 18? No. Let's just do, okay, 3.14 divided by 18, that's like 6, a little bit less than 6. But what is it exactly? So yeah, it's gonna be like it would be like 0.5. Let me see. Okay. 0.5. Let's see, 5.5? No. 5. Let me think. Can I get it to 2 decimal places? Can I get it to the 100th place? 0.5. Hmm. Oh, it goes into it. Oh. Wait. Pi divided by 18 would already be 0.5. No. How many times does... No, it would be less than 0.5. How many times does 18 go into pi? Hmm. Actually, would it be 0.5? No. It would be 1/6. It would be less than 1/6. And 1/6 is... Oh, fudge, bro. What is 1/6 in decimals? Bro, I don't know. I'm actually embarrassing myself. 40, 36. So it would be like 0.16. Yeah, 0.16 and 2/3, which would be 6.166. So I'm gonna say 0.17, but that's only 1/6. So it would be oh no, it would be more than 1/6. Okay. It would be, yeah, it would be one. Okay, so it would be more than 1/6, but less than 1/5. So if it was 3, it would be 1/5. No. No, if it was 3, it would be 1/6. But since, yeah, okay, so, yeah, if it was 3, it would be 1/6. But since it's more than 3, it's less than 1/6. Or, sorry, more than 1/6. Because if the number on the bottom gets smaller than the number increases, then the total increases if you're doing it with fractions. So let me think here. It would be 17.17.1. This is the bro. I feel dumb. Uh, 0.17. I'm gonna guess. Wait, am I? Oh, yeah, yeah. I did do that correctly, right? Point oh, 1/6 is 0.17. Okay, I am gonna guess. Yeah, I'm gonna guess 0.17. Final answer. Let's do it. We got pi. Okay, no, that's not what I meant to do. We got, wait, graphing? Oh my. We got gra scientific doesn't have what? Bro, you have what is this called? You have factorials, but not oh pi. Pi's right there. Pi divided by 180. 0.17, final answer. Ah, I forgot to carry the decimal. But besides that, I got it right.
Unity's trig
Okay, I need to not waste time on stuff like that.
functions all work in radians, as we'll see in just a bit. But first, I'd like to point out that if we're creating a 3D game, then the convention in Unity is that at 0 degrees on the y-axis, a character faces forward along the z-axis. As we increase the angle, the character rotates clockwise, so we could represent this with a circle like so, which is of course different to the unit circle we've been using, where 0 degrees represented a direction along the positive x-axis, and the angles increased anti-clockwise. Let's put these two circles side by side. The conversion between the two is very simple. It's just 90 minus theta. Take, for example, 180 degrees from this circle. To convert it, we just do 90 minus 180, which is equal to negative 90 degrees, which is of course the same thing as 270 degrees. And converting the other way is exactly the same. 90 minus 270 equals negative 180 degrees, which is the same thing as positive 180 degrees.
Okay.
Keeping this in mind, I'm going to go into unity degrees, which is the same thing as positive 180 degrees.
Okay. Yep.
Keeping this in mind, I'm going to go into Unity, where I have a simple player setup, just made out of a capsule and holding a little cube object, which you can maybe imagine as some sort of weapon, just to show what the character's forward direction is. I'm going to right-click, create a new C# script, and I'll just call this trig test, and I'm
Okay.
going to apply that to the player object. You can then open that up, and in here, I'll start by creating a public float called angle in
Yeah, I
degrees,
don't think I need
and
to
then in
go
the update
in engine to do this. To take this in, to absorb it. So
method, I want to get a direction from
I'm
that
just gonna
angle. So we start
watch.
to do this, we can create a vector. So update method, I want to get a direction from that angle. So we start to do this, you can then open that up. And in here, I'll start by creating a public float called angle in degrees. And then in the update method, I want to get a direction from that angle.
Okay. Sure. How do I do this? I want to get a direction from the angle, so 0 would be forward. Okay, it depends on what he wants the direction to be. Like what he wants the output for direction to be, you know? Like, is he gonna say forward, forward, backwards, left, right, or is he gonna do? Okay, I have to remember my hand is not always in frame here. Is he gonna do forward, backward, left, right, or is he gonna do north, south, west, east? Like, find a direction. So, what? You just do. Okay. So you just transform. What is it? Transform dot. Oh, how do you even get the angle? Transform dot angle. Rotation. Sorry, transform dot rotation dot uh x. Transform dot rotation dot x. Like you have to print out some sort of direction or he's not actually. Yeah, or he's not or he's not getting the direction. You know what I mean? So if it's 0 from so just say 0 to how do you divide it by 3? Oh, okay, yeah. So you just say negative 60. It depends on if you wants to do in radians or not. So you can just say negative 60. Oh, no, 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 no. You say, oh, that's just going to be a bunch of if statements, though. But isn't that what you have to do? If transform.rotation.x equals, oh, sorry, is greater than negative 30? Oh, okay. No, no, no. It would be greater than 330? but less than 30? I would just say negative 30. Greater than negative 30, but less than 30. Print north, and then you just do the same for everything else. So you say if it's greater than 30, but less than 60, it is northeast. Okay. I'm going to
We start
find
to do
out
this,
how he
we can
does it.
create a vector. So let's make this a vector 3, call it direction is equal to a new vector 3. And now we use cosine and sine. So mathf.cos of angle in degrees, and we need to convert this to radians because all of the Unity trig functions work in radians, as I mentioned earlier.
Ah,
So we do that by multiplying by
got it.
pi over 180. Well, alternatively, Unity's actually gone and stored this conversion factor inside a variable called degrees to radians, which is a little bit easier to remember. So you can just write multiplied by mathf dot degrees to radians. And you can see this just stores the value of pi over 180.
Dag 2
All right.
rad. Dag 2
Then on the
rad.
z-axis for this vector, let's have mathf dot sine of angle in degrees multiplied by, once again, mathf dot degrees to radians. All right.
What?
Now, just to see what this direction looks like, let's
What? X and oh, Y. I
draw
see.
array. So debug.drawArray from transform.position in the direction that we calculated, and we can multiply it by some.
Angle in degrees. Public float. Why does he have to make that public, though? I mean, he's gonna set that, I guess? But it's gonna move on. That's not gonna work, I don't think. Because it's gonna move him. It's gonna move him twice whenever he sets the object, the game object angle the to whatever value he sets his variable as,
Distance, say 3, and then
I
let's give it a
think.
color, maybe color.green. All right, let's try that out. So I'll press play, and you can see the green line sticks out to the right along the x-axis, and as we increase the angle, it goes around anti-clockwise. Now, as I was talking about earlier, if we want that direction to point forwards at 0 degrees and increase clockwise with the rotation, as our character does, then we have to do that 90 minus theta conversion. So over here, before we multiply by degrees to radians.
Wait, what? But what? Oh,
Then we have to do that 90 minus and increase clockwise with the rotation, as our character does. Then we have to do that 90 degrees and clockwise. Now, as I was talking about earlier, if we want that direction to point forwards at 0 degrees and increase clockwise with the rotation, as our character does, then we have to do that 90 minus theta conversion. So over here, before we multiply by degrees to radians, in brackets we have 90 minus angle in degrees, and same thing over here, 90 minus angle in degrees. If we save that now,
what? Vector 3 direction equals oh, wait. Direction. Uh, what does that equal, though? Math f dot cosine. Angle in degrees. Angle in degrees.
In degrees, and same thing over here, 90 minus angle in degrees. If we save that now, we'll see that it works as expected.
But why does he put it on X and Z? What?
Now increase clockwise. Now, as I was talking about earlier, if we want that direction to point forwards at 0 degrees and increase clockwise with the rotation, as our character does, point the angle, it goes around and sticks out to the right along the x-axis, and as we increase the angle, it goes around anti-clockwise. Now, as I was talking about earlier, if we want that direction to point angle, maybe color the green line sticks out to the right along the x-axis, and as we increase the angle, it goes around anti-clockwise. Now, as I was talking about earlier, if we want that...
Oh, I see. I see what he's doing. So he's setting, I see. He's setting the direction as an X and Z value rather than, I mean, is there an easier way to do that? Can't you just set it as one or the other? I mean, he had it as a vector 3. Can't you just set it? You can.
Direction
Or
to point
can you?
degrees. In brackets, we have 90 minus actions. So debug.drawRay.
Oh. Why does it have to be a vector 3 now? What? Why does it have to be a vector 3? If you do x, 0, wait, what? Why does it have to be vector 3? I'm not going to open the engine for this episode. No shot I'm going to open it, bro. Why does it have to be a vector 3? If I do x equals 0, z equals 1, I guess. And we're doing the unit circle one like he did here. Like if I did 1, 0, 0, if I did x equals 1, so direction, I did 1, 0, 0. It would draw it out forward, right? Or in the x direction, it would draw it out to the right. Am I missing something? Wouldn't it draw it out to the right? Huh. I don't know.
From transform.position in the direction that we calculated, and we can multiply it by some distance, say 3, and then let's give it a color, maybe color.green.
I think it would.
Right, let's try that.
And also, what would happen if you set it to 1, 0, 1? What would happen if you did that? Vector 3?
So debug.drawRay
Do I actually need
from
to...
transform.position in the direction that we calculated, and we can multiply it by some distance, say 3, and then let's give it a color, maybe color.green. All right, let's try that out. So I'll press play,
I'm
and we can see
curious
the
now,
green line
actually.
sticks out to the right.
So this is just saying x equals 0, or x equals 1, z equals 0.
Along the x-axis, and as we increase the angle, it goes around.
Okay, and then now it's doing the different vector things here. If you had it set to 1, 1, though, it would do this, but then it would, oh, distance, okay. If you had it set to 1, 1, 1, 1, okay, so it would point this way. At what point on a unit circle does it equal 1, 1? It doesn't, but it would equal the same at 90 degrees. Well, okay, let me think. They equal the same thing at 90 degrees. The sides of the triangle, of the right triangle on the unit circle equal the same thing when the hypotenuse is at 90 degrees. Is that even, I don't even know if I'm using the right word there, but I'm pretty sure, yeah, 1, 1, okay. And then let's try 0.5, 0.51. Okay, so it would be 1, but then 0.5? Okay, x would be 0.5. X would be 0.5, so it would be up here. Huh, I guess it does have to be a vector. I guess. That is so weird. Direction. Direction. Hmm. Let's try 0.251. So it would be here. Okay, let's try 3, 2. Sorry, 2, 3. Actually, for the sake of simplicity, let's just do 2, 1. It would be here. Okay, let's do 2, 3. Here. So, a lot of things would equal the same thing as long as the ratio, is the same, then the direction would be the same. So 1, 1 would be equal to 2, 2, which would be equal to, I mean, yeah, so really the value doesn't matter past 1, right? Which is why I guess he's doing the unit circle method here.
Anti-clockwise.
All right, fair enough.
So same thing over here, 90 minus, as expected.
Okay,
We save that
and
now.
then now
We'll see that
he's just
it works as
changing it to
expected.
the unit circle thing
Now, recall
here.
that when we actually plotted sine theta and cos theta, we saw that cos 90 minus theta was equal to sine theta, and likewise sine 90 minus theta was equal to cos theta. So if we wanted, we could remove this 90 minus business over here and here, and instead just swap cosine with sine, so make this sine on the x-axis and cosine on the y-axis, or in this case the z-axis, and you can see that this is exactly the same thing.
Wow.
Alright, so that was the first problem. Let's now look at the second problem of getting an angle from a direction.
Sure.
So I'm going to use the example of getting the keyboard input for the arrow keys and using that to find the character's rotation. So say we get a vector 3 called the input direction, so it's equal to a new vector 3, and on the x-axis
Hmm. Is he going to do left, right, or is he going to do... Okay. What was it? Get axis raw. Then that has to equal something. Get axis raw left, or is it negative x? I
So we
don't
get
remember.
a vector 3 called the input direction. So it's equal to a new vector 3. And on the x-axis, we have input.getAxis raw, horizontal.
Horizontal. Sorry, horizontal. And then you set the... What is it? So vector 3 get axis raw horizontal, so that's x, and then the other one is z.
On the y-axis, we have 0, and then on the z
Then input dot get axis raw vertical.
axis input.getAxis raw,
Got it.
vertical. And we can now normalize that to give it a magnitude of 1. So it's a proper direction vector.
Uh-huh.
And then we can move our character around with transform.translate input.
And I forget why
On the
you need
y-axis,
to
we have 0,
normalize
and
that
then on the z.
exactly. He did teach this before. He did talk about this before. But um, I forgot it, or I guess I'm just getting it refreshed for me here.
Axis input.getAxis raw,
It's not like I forgot it. It's like I haven't thought about it in a while, I guess.
vertical.
Okay,
And we can now
what does this do here? And why, my real question is, why does this need to be normalized? I already asked that. Returns the value of the virtual axis identified by axis name with no smoothing filtering applied. I would have to try that out, maybe. Input.getAxis raw horizontal and vertical. And then I'm touching my mic. That's not good. And then I would have to print it out. Like why, like in what circumstance would it not equal 1?
and we can now normalize that to give it a magnitude of 1.
You know what I
So
mean?
it's a proper direction vector. And then we can move our character around with transform.translate input direction multiplied by time.delta time. Let's just give it a speed of 5, say. And then this should be relative to the world. Okay, so if we try that out, let's press play. You can use the arrow keys now to move the character around.
Yippee.
Okay, now to actually set the rotation, let's create a float called input angle, and we'll set this equal to mathf.atan2, passing in the y and x components of our directional vector. Well, in this case, since we're using a 3D vector, it will rather be the z and x components. So input direction.z and input direction.x. And atan2 returns the angle in radians, so you can convert from radians to degrees, of course, by multiplying.
Mm-hmm. A10 2. Sure. Input angle. Is it that easy? Isn't it instant, not smoothing? I'm thinking it's going to be instant and not smoothing. A10-2Z. What does that do again?
Multiplying
I don't
either by
remember.
1/80 of a pi, or simply using
But I would like to finish this episode before midnight. I guess it doesn't really matter.
radians to degrees. Okay. Let's by 1/80 of a pi, or simply using mathf dot radians to degrees.
Oh, I see. Okay. Input angle Z over X. What would that do?
Okay, let's then write transform dot Euler
Is
angles
he
is
doing
equal to
that
vector
right,
3 dot up
actually?
multiplied by the input angle.
Tangent is x. Oh. Yeah.
So we're just rotating our character around the y-axis by the input angle.
Oh. Tangent is y over x. Okay, I see.
If we save that,
Tangent is y over x. Wait,
and press
I
play,
don't think it's going to
we
work.
can move around, and we'll see that the rotation isn't quite corresponding correctly to the input. By now, of course, that's no mystery to us. It's this whole 90
Yeah, no, it's because you swapped
minus
these.
story again.
I'm pretty
So we just
sure.
add 90 minus our angle over here, and that should now work correctly. So we move around, and we can verify that it is working how we want it to. The last
Wait, shouldn't this be x though? A10 to A10, which converts the it's the opposite. So it would be x over y. And z is this one, this way. So, okay, I'm confused.
thing I want to mention is that similar to how
A10 to A10 to. Vector 3 dot up times input angle up. Vector 3 dot up. Why
we
would it be vector 3 dot
direction
up?
dot z, when you convert from radians to degrees, of course, by multiplying. Okay, so we just right transform dot Euler angles is equal to vector 3 dot up.
What?
Multiplied by the input angle.
Vector 3 dot up. Why would it be vector 3 dot up, though? Why would it be up?
Let's then right transform dot Euler.
Why would it be up? Why would it be up? I'm confused. Z. This is X, this is Z, this is the input angle. Okay. Z. Vertical. And it turns it into degrees. So this would be A tan 2. Let's just do positive in my head here. Both positive. So the A tan doesn't really matter. So it'd be X. This would be X. That would be Y. So vertical would be 1. Okay, and then I don't get why you did that. Okay.
Euler angles is equal to vector 3 dot up, multiplied by the input angle. So we're just
And I don't know why
rotating our
that's
character
vector
around the
3.
y-axis by the input angle.
Oh, that's why. Rotating around the y-axis. That's that makes sense. Um, I guess I just wasn't paying attention.
Degrees, since the degrees of correction, 3D vector will rather be the z at x, the y called input angle,
Maybe he explains it
and we'll
here
set
and
this
I
equal to math
also
f.
wasn't paying attention. Returns the arctangent of f. The angle in radians whose tangent is f. Okay. Oh, okay. Atan equals. Okay. Okay, to get the angle. Okay. So Atan gets an angle. Okay, wait. Oh, okay. Okay. I'm thinking of something else. Am I? Tangent is y. Okay, so none of this changes. So this doesn't, there's no x over y. I'm just completely tripping. Tangent of y over x. Tangent of, okay. The tangent of the angle is y over x. So nothing is y. Nothing is x over y. I just was completely tripping out. What would that be? What would the inverse be? Would it be 1 over tangent? Okay, let's say... Okay, let's say 90. Okay, let's say, no, let's say 0. Let's say it's at 0. Okay, so y is 0, x is 1. So that would be 0. The other one would be infinity. Well, technically undefined, but approaching infinity. And then it would, okay, but it already has that here. So all that does is rotate it by 90 degrees, right? That would be 1, 0. That would be negative 0, negative 1. That would be negative 1, 0. Yeah, all that does is rotate it by 90 degrees. So I guess doesn't really matter. I think it does, right? Because if we do small, no, no, it doesn't. No, it doesn't. Or does it? Positive. No, it does some weird stuff. Here. Oh, it does it. Okay. It just mirrors it, I guess. It would be like a mirrored unit circle. Except this would be positive. Okay, wait. It would be. Is there a reverse tangent? Okay, either way I was wrong. I'm not gonna look that up. It doesn't really matter. I shouldn't really care. It does not. Okay. Tangnet. Is there an inverse tangent? Inverse tangent formula, arctangent. No. Um, that's not what I. No. Is there a flipped tangent? Ah, my watch later. Um, hmm. Yes, either way, he was right. Let me think.
Let's just give it a speed of be the z and x components. So input direction dot.
I swear, like, when I make a game, this is going to be immediately what I do here. Um, this, this right here, I'm gonna make into a method right away. Like, right away. If there's not already a built-in one. Okay, I'm tired. Um, got it. Tangent goes y-x. Would there be any use for an x over y? No, right? Wouldn't it just would it just be 1 over tangent? Would it actually just be 1 over tangent? If you flip these, that's okay. That would be x over y. Tangent of an angle, so a tangent of. Okay, this hypothetical reciprocal tangent? Is there a reciprocal tangent? Yes. I forgot about that. I actually forgot about that. So when is this used even? Ah, cotangent. All right, so let's just say 0. Cotangent would be, okay. This one is 0. Cotangent would be undefined. This one is, they would be the same, actually. So what would the graph look like? The graph would look like, cotangent. The graph would look like, um, what the fudge would it look like? Oh, it would like come down here, right? It'd be like this, but flipped along the y-axis. No, along the x-axis, I guess, right? No. Okay. It would still be, no, it would be flipped both. Flipped along the x and y. So it'd be flipped here, and then it would be flipped over there. So it would be coming down from here. Because cotangent would be uh, x over y, which would be 1 over 0. Then it would slowly go down to 90, which would be 0 over 1. No, it would be some weird stuff, actually. It would be moved over. Flipped, and then moved over. 90. Okay, it would equal 1 in the middle. X would be 0. No, X is 1. So X over Y would be, yeah, okay, then it would come down. Then it would be 1, sorry, 0 over 1. Then it would go back down. Let's see if I'm correct. Cotangent, cot graph. Yep, That's what I predicted, I think. Okay. Can I get a decent graph around here? Can a man get a decent graph around here, please? Um, we did work with radians in regular trigonometry for sure. I just completely forgot about it. Pi 2 pi. Okay, so this is 180. Okay, why do I keep doing that? So this is 180. So, yep, 90, boom. Down, over, down. Yep, interesting. Interesting. I guess it would just, is it just flipped? Yeah, it's moved over and flipped. Moved down 90 degrees and flipped. That's it. Because he's not showing the other parts. It would just be a repeat of this. Okay.
-1 on the graph, we'll notice
Why did I feel the need to answer that burning question?
dot translate
Whatever.
input direction
It's
multiplied by time dot
actually
delta time,
okay.
which
I'm
is given a
learning.
speed of 5, say, and then this should be relative to the world. Okay, so if we try that out, let's press play. You can use the arrow keys now to move the character around. Okay, now to actually set the rotation, it will rather be the and 8 and 2 returns the angle in radians, so we need to convert from radians to degrees, of course, by multiplying either by 180 over pi, or simply using mathf dot radians to degrees. Okay, let's then write transform dot Euler angles is equal to vector3 dot up, multiplied by the input angle, so we're just rotating our character around the y-axis by the input angle. If we save that,
I'm probably going to put this all in a single
press play,
method.
you can move around, and we'll see that the rotation isn't quite corresponding correctly to the input. By now, of course, that's no mystery to us. It's this whole 90 minus story again. So we just add 90 minus our angle over here, and that should now work story again. So we just add
Sure.
90 minus our angle over here, and that should now work correctly. So we move around, and we can verify that it is working how we want it to. The last thing I want to mention is that similar to how we could get rid of the 90 minus in this example over here by swapping sine and cosine, you can also get rid of the 90 minus over here by swapping the two components. So I can swap x with z, 90 minus over here by swapping the two components. So I can swap x with z, and if we save that now, you'll see that it works in exactly the same way.
Wait. What? So why does he have to add the 90 again? Oh, because it... Okay, I see.
Here, by swapping...
Because this is working on the unit circle, not the unity circle. Like he showed over here. Trig circle. He calls it the trig circle and not the unit circle. Okay, and okay, and why does switching them work? Again? Oh, because it just, I see, because it just rotates it by 90. Understood. Understood. It just, yeah, because x1, y0, um, is equal to y1, x0. Got it, got it.
So we just add 90 minus our angle over here. The last thing I want to mention is that similar to how we could get rid of the 90 minus in this example over here by swapping sine and cosine, we can also get rid of the 90 minus over here by swapping the two components. So I can swap x with z, and if we save that now, we'll see that it works in exactly the same way.
Perfect.
Okay, that is everything for this video. Over the next few
Amazing.
episodes, we'll be working on our second mini project to put all the stuff we've covered so far into practice. Until then, cheers.
Oh boy! Next time.
You can sell this $5 spatula on Amazon and compete with hundreds of other spatula sellers. Or you can sell digital products on Amazon and compete with almost no one. You see, I use a brand new Amazon platform that's banned the sale of physical products.
Hello.
That was crazy. That was insane. That was so cool, bro. When he bent the spatula like that, that was so cool. Also, you could sell this jacket on Amazon. Actually, that's an expensive jacket. You could sell this sheet on Amazon for two cents and compete with thousands of other people. Or you could sell digital products which have no real value and scam people out of their money. Isn't that crazy? What a deal. Okay, that was it for today's episode of Learning Game Dev. That was episode 6. Did I do it with my right hand? Did I do? Yes. That was episode 6. I will see you tomorrow for episode 7. Thank you for watching.